My name is Bruna Coutinho, and today I'll be presenting my final thesis for the Mechanical Engineering Department of the Universidade Federal de Santa Catarina, the UFSC. This work is entitled Measurement and Analysis of the Aerodynamic Pressure Field at a Rocket's Nosecone Surface. My advisor was Professor Amir Oliveira Jr., and this work was developed along with Apex Rocketry team and presented in March 2021. So we will begin with the agenda of today. We'll start with a brief introduction of the issue, followed by each and every objective of this work. In the same order they were developed during the work, they will be presented today. Lastly, some conclusions and some future work recommendations. I will begin with the introduction. It is known nowadays that the space industry is worth more than $345 billion, and it has technology advances that impact different areas of the economy, as well as investments from different sources, such as government and private. Some of the main space applications today are the International Space Station, telescopes, and satellites, for instance, and they all have in common the same factor: rockets, which are the rockets that launch them in actual space. Bringing to the context of the UFSC, some laboratories have some space application experiments. For example, LabCal, which is the heat pipe laboratory, has a partnership with Brazilian Space Agency, the AEB, and has the opportunity to launch its experiments every 2 years to actual space. The Space Lab is another laboratory that developed the Floripasat-1, which is a CubeSat that was launched in China in 2019. But even then, there was a lack of a specific rocket team, so in October 2018, a group of students funded Apex Rocketry. During its first year of existence, Apex Rocketry was able to successfully design, build, and launch its first project, the Brava A11 rocket. However, there was still a lack of deeper studies and analysis of the aerodynamic field, especially on focusing on its nosecone, which is highlighted in red. So that's why the idea of this project emerged. Now for the objectives of this work. The general objectives of this work are highlighted and consist on the aerodynamic study of the rocket, focusing on its nosecone, and a sensor system development to measure the angle of attack of the rocket in real time during flight. Other specific objectives are a prototype design and manufacture of the nosecone to be tested in wind tunnel, in which will be compared different measurement methods, and also the development of an angle of attack model to be used by the sensor system to measure the angle of attack of the rocket. So now we'll begin with the aerodynamic study of nosecone. The project studied during this work was Armação A22 project, which was the second project developed by Apex Rocketry after the Brava A11 project. This project was developed between the years 2019 and 2020. It has a solid propulsion system, and its features can be adapted depending on which mission the rocket is competing in one of the many intercollegiate competitions that happen in Brazil and Latin America. Here I would like to highlight some information. First, the von Karman nosecone profile chosen by the team for this project and its final measures shown in figure 3. Another highlight is the launch rail departure velocity of 24.7 meters per second, which will be important later on, and I will explain why. The aerodynamic study started with the aerodynamic forces and coefficients. The main force acting on a rocket is the total aerodynamic force, Fa, and it can be decomposed in two different ways. The first way, it can be decomposed in a normal force, Fn, and a tangential force, Ft, in which the tangential force is parallel to the center line of the rocket. The second way, it can be decomposed in a lift force, Fl, and a drag force, Fd, in which the drag force is parallel to the velocity, Vcm. Aerodynamic forces are usually written in function of dimensionless coefficients. For instance, the lift force can be written in function of the lift coefficient, Cl, also in function of the dynamic pressure, Q, and the reference area, S. In this case, the reference area is the rocket cross-section, which is also the same area of the nosecone base. The dynamic pressure is expressed in function of the airflow velocity and the airflow density. The next part studied were Mach number, Reynolds number, and boundary corrections. So for subsonic speeds, which means Mach number lower than 1, the viscous drag is the main kind of drag acting on the rocket, so it can be estimated by the friction drag coefficient, which is the CDF shown in the equation below. This coefficient is written in function of the Reynolds number, which is a factor widely known in the aerodynamic field. The Mach number is expressed in function of the sound speed. For the conditions of this work, the Mach number was calculated in 0.1 and the Reynolds number in 1.3 times 10 to the 5th power. For boundary corrections, it was considered solid blockage correction that can be written in function of a shape factor K, the model volume, and the wind tunnel's section area. For the shape factor and the model volume, it was used some references for revolution solids, which is the case of the rocket. The correction was then applied to the measured velocity of the wind tunnel of 26.2 and the final corrected velocity was of 26.1 meters per second. This velocity is in the same order of the launch rail velocity that I highlighted before. So every analysis and result of this work can be considered to the first stage of flight, the launch rail departure. The last topic studied at the aerodynamic study was the pressure field, focusing on the center of pressure location and the normal force. According to Hartmann, one of the references studied, he proved through his work that the normal force can be directly substituted for the normal force coefficient, Cn alpha. He also showed through his work that Cn alpha for the nose is always 2, regardless of the nose shape and profile, and for the rocket body is always 0. To find the center of pressure location of the A-22 rocket studied in this work, we follow some steps. First, we go to 0 every term corresponding to the rocket body, such as Hartmann described. Then we also equal to 0 every rocket part that the A-22 project doesn't have, such as the conical shoulder and conical bolt tip. So, afterwards we need to find the von Karman profile center of pressure location, which according to references equals to 0.5 rocket length. And then we have the final formula. Now we're going to the prototype design and manufacturing part. The prototype was designed based on the already existing nose model of the A-22 rocket, with some additional modifications. It had 3 rows of 10 orifices, each separated by 120 degrees drilled in it. It is important to notice that row A was aligned with the center line of the wind tunnel's test section. Rows B and C were not, however, they were symmetric towards this line. In Figure 9, you can see the final result of the complete Nosecone experimental setup, and in Figure 10, a scheme of one of the 30-hole capillary hose experimental setup, in which the capillary tube is attached to each hole, and a silicone hose attached one side to the capillary tube and to the other side it is connected to a water column manometer, which is one of the 2 different measurement methods used in this work. Here we have the stages of prototype design and manufacturing for the Nosecone. First, in Figure A, we have the 3D model designed in SolidWorks based on the existing model of A-22 rocket with the modifications of the orifices. In Figure B, we have the 3D printed Nosecone mode used to do the fiberglass lamination, which is shown in Figure C, and then this lamination was sanded and painted as shown in Figure D, and also it had the 30 holes drilled in it to achieve the final result. So now we're following to the next section called Sensor System Development. So the sensor model chosen for this work was a differential pressure transducer from NXP Semiconductors. This model had a pressure range of plus minus 2 kPa and an accuracy of 2.5% of full-scale span, which, according to the manufacturer, equals to 100 Pascal. Therefore, a previous simulation done by Apex Rocketry team during the A-22 project development was used to choose these 2 points. The simulation had parameters for extreme scenario of flight conditions, such as a Mach number of 0.73, temperature of 300 Kelvin, and angle of attack of 10 degrees. The extreme scenario condition was chosen so this sensor system will be able to work at any stage of flight of the rocket. Now, analyzing the data of the graphic, we can notice that the curves for 60 mm from the Nosecone tip and 80 mm of the Nosecone tip, they have similar geometry and a difference between them of around 2 kPa, which is the pressure range of the sensor. The 16 mm and 18 mm curves corresponds to orifices 3 and 4 out of the 10 drilled in the nose cone, and this turned out to be an iterative process, so these points will change later on. I will explain why. However, for now, this was the starting point of this process. The next step was the wind tunnel tests. So the wind tunnel test began with the placement of the experimental setup inside the wind tunnel. In figure 16, you can see the side view of it, and in figure 17, the rear view. As I already mentioned before, there are two different measurement methods used in this work for the wind tunnel tests. The first one is shown in figure 18, which is a water column manometer, and the second one is the sensor system developed, shown in figure 19. The measurement procedure of the wind tunnel tests occurred in three different stages. The first stage consisted in only the manometer as the measurement method for 0, 5, and 10 degrees of angle of attack. The manometer was connected to each and every orifice from 1 to 10. The second stage consisted in only the sensor system measuring the data. It was also measured for 0, 5, and 10 degrees of angle of attack, and as I mentioned before, orifices 3 and 4 with the iterative process changed to orifices 3 and 9 for pressure difference measurement. I'll explain later why this change happened. And the third stage consisted in a combined analysis of the two methods measuring at the same time, both the manometer and the sensor system, also for the same angle of attack for 0, 5, and 10 degrees. This time, the measurement occurred measuring the pressure difference between the different rolls A, B, and A and C. This was possible due to a Y connector that divided the nose cone air inlet into the two axes, one for the manometer and another for the sensor system. This wind tunnel results consisted in the water column manometer measurements, and here you can notice that points 1, 2, and 10 show inconsistencies. The first and second orifices located at the nose cone tip, it was really hard to achieve during the manufacturing process shape and format accuracy. The 10th orifice, since it is located at the part of the nose cone that no longer follows the von Karman profile, instead it follows a straight line to attach to the rocket body, a float attachment may have happened at this point, so this point also showed some inconsistencies. Therefore, orifices 1, 2, and 10 were disconsidered in further analysis and calculations. Another important point here is that the pressure scale is in the same order of the sensor accuracy, around 100 Pascal. So instead of orifices 3 and 4 for pressure difference measurements by the sensor system, they were chosen the points 3 and 9 for the highest pressure difference possible. As I said before, this was an iterative process, and from points 3 and 4, they were changed to points 3 and 9. These points 3 and 9 were measured by the sensor system at the second stage of wind tunnel tests. Here, the sensor system measured the pressure difference between points 3 and 9 in the same row. And as you can see, the higher the angle of attack, the higher the difference noticeable between rows A and B and A and C. However, we can also notice a difference between rows B and C, which can be due to the hypothesis already mentioned in the last stage of construction issues, especially at the nose cone tip, but it can also be due to the hypothesis of alignment issues, which means the alignment of the experimental set inside of the wind tunnel that could be causing an horizontal angle. Considering this is an electronic system, there can also be some calibration issues causing this float asymmetry between rows B and C. And last but not least, regardless of the different scale between this pressure difference and the sensor accuracy, it shows the same behavior expected, which is a good result for the sensor system. After the two first stages of wind tunnel tests, a preliminary angle of attack model was developed. However, it did not turn out as expected because it did not show a direct comparison between methods, even when comparing different angles of attack or different roles. So a new set of tests was required. Go to the last stage of wind tunnel tests, which was the comparison between measurement methods or combined analysis. First, I would like to remark that the sensor system results are divided by 10, so the scale is similar to the manometer results. Also a reminder that in this stage the roles were compared, so in figure 29 it is shown a comparison between the rows A and B 4 points 3 and 9, and in figure 30 the comparison between rows A and C 4 points 3 and 9, the same points measured by the sensor system in the last stage. In this stage, a comparison between methods was performed in the wind tunnel test. The lines correspond to the sensor measurements and the points to the manometer measurements. We can notice that despite the difference between the scale of both methods, their behavior is similar, and the higher the angle of attack, the higher the measured values. Another topic to analyze here is that comparing the pressure difference between rows A and B, it is higher than between rows A and C, which, coming back to the results in the last stage, it also shows results higher for row B than for row C. This fact reinforces the hypothesis of calibration issues of the electronic system and/or the presence of an horizontal angle of attack inside of the wind tunnel due to alignment issues. Again, despite of the sensor accuracy of 100 Pascal and the scale being different, it shows the same tendency and behavior as the results measured by the manometer, which is also a good result for the sensor system. After this combined analysis, we were finally able to develop an angle of attack model. This model works according to the following scheme. A sensor is placed to measure the pressure difference between two rows A and B, and another sensor to measure pressure difference between rows A and C. Here, rows A and B are shown to illustrate. So the sensor measures the pressure difference between two rows and of the same point. The sensor data in the first part of the model is converted to the manometer data scale, which is considered a base scale with the correct values of this work. Then for the second part of this model, the manometer data are converted to a value of angle of attack, which is the angle of attack of the rocket measured during flight in real time. An assumption was made for this model, considering that any discrepancies between rows A and B and A and C data are due only to calibration issues in order to minimize the presence of any horizontal angle. For the first part of this model, a scale-adjust equation was found comparing the sensor data and the manometer data. So this equation is almost linear, and it works as the following way. So the sensor data is measured, delta PS, and it serves as an input for this equation, and the equation returns the value of delta PM, which are the pressure differences converted to the manometer data scale. For the second part of this model, the corrected values to the manometer scale serve as an input to the angle of attack factor H, that consists in the sum of the modules of the pressure differences between every row. So the pressure difference between rows A and B and A and C are measured by the sensor system, and the pressure difference between rows B and C are calculated as the following equation. As I already mentioned, this model was developed for orifices 3 and 9, so in order to be used during flight, the sensor system had to be placed either in orifices 3 for rows A and B and A and C, or in orifice 9 for rows A and B and A and C. This graphic shows a function in parts, so it is noticeable that the second part of the function has the same inclination, which is a good result and indicates that this model can be expanded for other angle of attacks and other Mach numbers. As mentioned before, this model corresponds to low Mach numbers, which means low velocities in the order of the launch rail departure velocity that corresponds to the first stage of flight. However, this model can be expanded through more experimental tests for more orifices, which can give a more accurate curve instead of a function in parts. It can also be expanded through simulations for the same conditions and simulations for higher Mach numbers. Simulating for higher Mach numbers means that this model can be applied to other stages of flight, and it can be used during the whole flight of the rocket. In figure 32, we can see a scheme of how the sensor system should be placed inside the rocket in order to use this model. So a first sensor should be measuring the pressure difference between rows A and B for the same point, in this case 0.3 for example, and a second sensor should be measuring the pressure difference between rows A and C. For now, it is only possible to use this model for points 3 and 9, due to the tests already performed. However, as I already said, this model can be expanded so it can be used for more orifices and more stages of flight. Now for the conclusions of this work. Since every section of this presentation corresponded to an objective of this work, all the objectives were concluded, considering the main ones as the aerodynamic study of the rocket focusing on its nose cone, both through literature and experimental analysis was concluded. The development of an angle of attack model to be used during flight in real time with the sensor system development was also successful. Other manometer results and sensor results showed distinctly the different roles of orifices A, B, and C, despite of the discrepancies between rows B and C. Even though the first results did not match exactly the manometers, a combined analysis was performed, and this analysis provided the data for the angle of attack development to be used by the sensor system also developed through this work. Finally, calibration issues and horizontal angle were the main error sources of this work. Lastly, for future work recommendations, they were separate between experimental and numerical recommendations. So for the experimental part, it is recommended to rebuild the nose cone prototype using a more accurate manufacturing process to avoid any alignment or construction issues. It is also recommended to improve the method of alignment of the model inside the wind tunnel to avoid any horizontal angle. To perform a new set of tests at the wind tunnel to acquire data for more angles of attack in all the orifices, especially for improvement of the model of angle of attack, and to calibrate the sensor system with known values of pressure difference in order to avoid calibration issues. For the numerical part of future work recommendations, it is recommended to perform an equivalent numerical analysis for wind tunnel conditions to validate them with the data acquired in this work. To expand the angle of attack model to higher Mach numbers, therefore higher velocities, through numerical simulations that will already be validated by the data in wind tunnel conditions of this work. And lastly, to perform experimental and or numerical analysis comparing different nose cone geometries to determine the best choice for the next Apex Rocketry project. Especially because this project already had a chosen profile, the Coutinho profile, and I did not have the opportunity to compare different nose cone geometries. This is used throughout this work. And finally, I would like to thank you for your attention. I hope you enjoyed, and I'll see you next time.